Hey everyone, welcome back to the channel. And today we are going to solve reschedule meetings for maximum free time 2, which you can consider as a follow-up question after reschedule meetings for maximum free time 1. So I recommend you to check out that video first because the concepts here are a bit different from that particular problem, but it's just an extension of that problem. So it would be easier to understand this problem if you have gone through the first problem itself. Okay, so what constants here are different? So here we are also given a time period which starts from 0 and ends at 5, which is the given event time, right? Which is the given event time 5. Okay, so first event starts at 1 and ends at 2. The second event starts at 3 and ends at 5. Okay, so we have gaps available here before moving any events as 1 and 1 as well. Okay, so here, what the constraints which are different from the first problem? So here we are allowed to uh, move any event into any other position, let's say any other gap, by putting this event into some other place like this. Also, here we are only allowed to move at most one event. And so the constraints here are moving at most one event, and it's okay if we don't maintain relative order. Okay, so these two constraints which we will be focusing on for this particular problem. So let's understand this whole scenario by using just a simple example. So let's say our event timeline starts at 0 and 9. So this is our event time, which is the end of our event timeline. We have the first event which starts at 1 and ends at 2, and the second event which starts at 3 and ends at 5. So in this particular scenario, what are the free time we have right now without moving any of this event? So as we can see, we have 1, 1 here as well, and 1, 2, 3, 4. So the free time currently without moving any of these events we have is 1, 1, and 4. So the maximum of those would be 4 without moving any of the events. Okay, so what are the possible ways to increase this maximum free time? So the first approach would be the same as what we have followed in the first example. That means the first problem, which was the maximum available free time 1. So at that time, what we have done, we have moved this particular event in forward or backward direction. From that, we were able to get the maximum free time will be the summation of their neighborhood events. That would be 1 plus 1. So 2 would be the maximum free time. So if we have moved this event to backward direction, we would be getting this, we would be getting this gap here. So that would be 2, right? What if we have moved this particular event to forward direction? So by that way, we would be getting the maximum free time would be the summation of its neighborhood events only. That would be 2 as well. What if we move the second event in backward direction? So that would be the summation of its neighborhood event again. As you can see, that would be 5. What if we moved this particular event into forward direction? So from 3 to 5, we will be moving them to 7 to 9. So how much free time we can get by this operation? That would be 4 here. So that would be 1 plus 4, 5 again. So we have the first approach of moving events while maintaining relative order. That approach is nothing but just summing up the neighborhood gaps of that particular event. So as we have saw in this particular example, let's construct the gap array with event array to see for each event how much maximum free time we can get by summing up their neighborhood gaps. Okay, so our gap list would be 1, 1, and 4. Our event list would be 1 and 2. Okay, so let's see for this particular event, which is present at index 0. So for event which is present at 0, we would be summing up event which is present at 0 and 1, right? So we would be summing up which is gaps which is present at index 0 and 1. What for event 2? So we would be summing up event which is present at index 1 and index which and gap which is present at index 2. So for index which is present, so for event which is present at 1, we would be summing up this, this gap and this gap, which is the 4. So we would be summing up gap which is present at index 1 and 2. So from this particular operation, we can say that for event which is present at index I, we would be summing up I plus 1 gaps. Right? Let's move to second approach. Second approach would be not maintaining relative order. Okay. So what is the other way through which we can maximize the gap here? That would be simply taking this event out of this gap and moving it into some another gap. Let's say this, or anywhere here. So by that way, we can maximize the free time here by 3. So previously we were only able to maximize this first by moving this first event was 2. With just moving it into forward or backward direction with maintaining its relative order. So how to calculate the maximum free time if we move this particular event into some another gap? That would be the gap which are neighborhood to that event. So the gap which was neighbor of this event was 1 and another was 1 as well. But the event time period was also 1. So what we have done, the free time which we got by putting this particular event into some another place was the summation of all these 3 parts. So the summation of their neighborhood gaps plus the event time itself, right? So if we move this first event to some other place, we would be getting the maximum free time as summation of its neighboring gaps plus the event time itself. Let's consider this scenario called second event. How much maximum free time we can get by moving this particular event? We can move it into either direction, forward or backward. But let's say we have already considered that particular scenario in our first approach. So in the second approach, we are just left with choice of moving this event into some another gap. But is here you can see that we wouldn't be able to move this event into this particular position because this gap is not covering the event timeline. So this gap here is of length 1, but the event time which we have right now is of size 2. So 2 will be greater than 1. So moving this event is not possible. Okay. So by following the second approach, we can get the maximum free time as summation of its neighborhood events plus the event time period itself. But that only if that particular event has some available maximum sufficient gap at some other place, which should be greater than or equal to the event's time period. So here previously we would have gap of size 4, which was greater than the event time period. So 4 was greater than or equal to 1 before. But for this particular event, the maximum free time available, which was 1, which was less than the event time period itself, which is 2. But let's say for this particular event, how can we make sure that it has the maximum sufficient available gap, which is greater than or equal to its event time? So here we have to check that the maximum available gap, how to determine this particular part. So for any event, we have the, so let's see, our gap list at initially was 1, 1, and 4. 1, 1, and 4. When events were 1, 2. So let's say at index 0, let's say for event which is present at index 0, the maximum available gap. So for this particular index, the maximum available gap would not be its neighborhood events, but all events, which is after its neighborhood events or before its neighborhood events, right? How to get those all events gap? That would be nothing but if the event which is present at index 0, this is this particular event, we cannot take all the gaps which is present at index I and I plus 1. So we cannot take these two events. That would be this and this. So for any event which is present at I, we cannot take I and I plus one gap as their available gaps. We can take all the gaps which are present before I minus 1, but we cannot take I plus 1, but all the events after I plus 2 and I plus 2 itself. So for any event, we can take all the event list until I minus 1 and all the event list after I plus 2. Okay. And we would be seeing the maximum available gap from this combination of these two particular lists and see if the maximum available gap should be greater than or equal to event time. So by that way, we can make sure that if we can move this particular event to that maximum available gap or not. If yes, then we will be summing up all the neighbor gaps plus event time itself. So that's it for it. Let's move to coding part. First, we have to build our gaps list. So let's initialize our gap list. First gap would be the start time of the first event minus 0. Then we have to go through each event to find the gap in between. Let's initialize our size of events variable to length of events. That would be start time or end time. We can pick any of them. So let's pick start time. Then we have to find the gap in between the events by going through start time of current index minus end time of its previous events. For this condition to be satisfied, we have to initialize our index variable from 1. Okay, so what would be the last gap? That would be event time minus the end time of last event. Right, so this would be the last index of any event, and we have to minus that from our total event time. So that would be our last gap. Now we have to build a suffix max gaps list. What would be that? So that would be the maximum gap which we can get by moving from the last gaps. So let's say we have 1, 2, 3, 4, 5 as an index of gaps. Then we would be calculating what is the maximum gap which we can get from this 3 position to end of the list, from this 4 position to end of the list, from this 2 position to end of the list, right? It is required because let's say if we want to find the gap at position 0, then we, as we saw in the explanation part, that for that we have to see all the gaps which will be present in I plus from I plus 2 to n. So we can always combine the both list of the suffix max gap list and prefix max gap list and then sort it and then find the maximum gap which would be considered as a maximum available gap, but that would be a computationally expensive to calculate because the sorting operation will require us. Okay, so the sorting operation would be increasing our time complexity by n log n. If we just want to find that particular operation in O of 1, we can just find pre-compute that and store it in a suffix max gaps list and prefix max gap list so that we can get it when we require in O of 1 timing. So let's build our suffix max gap list. What would be that? So that let's initialize our maximum suffix gap as 0 and let's go to for I in range. Okay, we also have to calculate the size of gaps, which would be length of gaps, size of gaps. Let's initialize our maximum suffix gap list, and that would be 0 for I in range size of gaps. Here we would be storing all the maximum gap, which would be, if let's say we have to calculate the maximum gaps available from index I to n, then that would be maximum of maximum gaps suffix gaps list from I plus 1 and gaps of current. We can do it by this way, or let's say we just assign it to our variable I. Remember, we have to reverse this in order to calculate this maximum suffix gaps list from reverse position, from reverse direction. So that would be this much. Right. Let's build our prefix max gap list. We can also build it in the same way. We just don't have to reverse this thing. And let's change the naming. We have already completed that. Okay, maximum prefix gap, maximum prefix gap, maximum prefix gap, and maximum prefix gap list. So by this way, we would be calculating 0, 1, 2, 3, 4. We would be calculating maximum gap till 1, maximum gap till 1, maximum gap till 2, maximum gap till 3, maximum gap till 4. Now we have to check for each event. We would be applying first approach of just not reordering the events and moving it in either direction without picking it up and finding the suitable other gap which was not in its neighborhood. So we would not be doing that in first approach. We will be just moving ahead in here and there, and we just combining the neighborhood gaps. So first approach, that would be gap sum. We can anyways get it through I plus gaps I plus 1, right? So as we have shown in the explanation, the neighborhood gaps of this event would be I and I plus 1. So neighborhood gaps of event I would be gaps I and gaps I plus 1. So now we have to see maximum available gaps. So this is our first approach. How much gap we can get by using the first approach? This much gap we can get by using the first approach. What if we want to follow the second approach? For that we have to find the maximum available gap. Let's initialize it as a 0. So we have to see if the maximum, we have to check if do we have sufficient previous gaps. How can we check that? We can check that by through I minus 1, right? I minus 1 is greater than or equal to 0. That means if we have sufficient gaps available previously with it excluding its neighborhood gaps. So for that we have to check through with prefix gap list of I minus 1, right? Let's think about the further gaps which is available after the neighborhood events. For that we would be requiring I plus 2. How much that would be? That it should be less than or equal to size of gaps, right? Because this is the only available until the size of the gaps. So if that is available, then we would be calculating the maximum available gap. Sorry, this should be suffix and this should be I plus 2. So now we have to check if our maximum available gap is greater than or equal to current event's time. So end time of current event minus start time of current event. If it is greater than or equal to, then surely we can calculate our maximum free time or maximum gap. Let's set 0. Let's initialize it as a 0 as gap sum. Include it in a gap sum, right? Maximum available gap. No, we have to include the event timing, which would be freed up if we just pick that event and move it in our maximum available gap, right? Then we can just calculate our maximum gap by using the gap sum which we currently calculated, and we will just return maximum gap which is available by following either one of our approach. Okay, so this is accepted. Let's check out the full solution. Okay, so as you can see, it is working fine. Let's calculate the time complexity. So this would be O of n operation as we are going through each event. This would also be O of n as we are going through all events and their gaps in between. This would also be O of n. Remember, we can combine these two operations by just tweaking this index variable. Let's combine them. Here we have to just remove this reversed option, and we have to calculate this index by going through backward size. Right, so by this way also we can combine these two for loops and let's save some time of time complexity, somewhat of time complexity. So this was a small typo here. Let's run it. As you can see, it's accepted. Okay, so what about this? This would also be O of n. So let's combine O of n plus O of n plus O of n. So that would be O of 3 of n, which is equal to O of n as well. Let's talk about space complexity. So we are using the gaps array so that it would be required O of n as a space complexity that will occupy O of n. Another two O of n space would be occupied by this maximum prefix caps list and maximum suffix cap list, right? Yes, so that would be it. And finally, we can say that this is also would be O of 3 of n, but eventually we will be getting O of n as a space complexity as well. So yes, that's it for today, guys. Thanks for watching. Drop the comments if you have any feedback. Catch you guys in the next one. Peace.